Hello and welcome to this video about capacitance. We are going to look at the function of a capacitor, what capacitance is, what parallel plate capacitors are, and electrical potential energy and how that relates to capacitors. So a capacitor is a device that's used in different electric circuits, and it can perform a variety of functions like tuning the frequency of radio receivers or eliminating sparking in automobile ignition systems or storing energy in electronic flash units. The purpose of a capacitor is to store charge so that it can be used later for a specific application. One particular type of capacitor is a parallel plate capacitor. And here's an example of what happens with a parallel plate capacitor. We have two plates, and before a parallel plate capacitor is charged, this is what it would look like. There is no net charge on the plates. When we hook this capacitor up to a circuit and complete that circuit, we have this happening during charging. There's a small net charge on each of these plates. This has net negative and this one net positive. After charging, we see there is a greater net charge on each plate. And here, that charge is stored and can be used later for a specific purpose. In order to discharge this charge of a capacitor, basically the opposite of charging, that can be done when these two plates are reconnected with a conducting material. This capacitor will discharge. So a way to think about capacitance. Capacitance is the ability of a conductor to store energy in the form of electrically separated charges. So mathematically, capacitance is equal to the magnitude of the charge on each plate divided by the potential difference. And we represent capacitance with a capital C. In this case, the capital Q represents the magnitude of the charge on each plate. The SI unit for capacitance, you can see, it's going to be coulombs per volts, and we call that a farad, and it's abbreviated capital F. Most capacitors range from about 1 microfarad to 1 picofarad. Now, if we have a parallel plate capacitor and we do not have any material in between the plates, essentially a vacuum in between the plates, we can represent that by this equation. We can look at the capacitance for that kind of a capacitor as being equal to the permittivity of a vacuum. This epsilon, this Greek letter epsilon, represents permittivity, and the little 0 represents of a vacuum. So the permittivity of a vacuum is a constant, and it is 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. Just the permittivity alone, if it's not in a vacuum, it would change, obviously. If we had some material there, we could have the permittivity of some material, and it would be different from that of a vacuum. But if we're talking of a vacuum, this is the constant for that, and that's multiplied by the area of one of the plates divided by the distance between the plates. So the material between the plates of a capacitor can change its capacitance. Obviously, that shouldn't be a surprise. We call that material a dielectric, the insulating material here in between the two plates of the capacitor. It can be inserted to increase the capacitance, different kinds of dielectrics. Now let's take a look at electrical potential energy and how that is going to relate to a capacitor. Realize that it requires work to move charges through a circuit to the opposite plates of a capacitor. So work done on those charges is a measure of the transfer of energy. And we can look at the electrical potential energy stored in a charged capacitor as being equal to 1/2 times the charge on one plate times the potential difference. Let's look at a sample problem. Let's say we have a 3.0 microfarad capacitor connected to a 12-volt battery. What's the magnitude of the charge on each plate of the capacitor? And how much electrical potential energy is stored in the capacitor? Well, I know my capacitance is 3.0 microfarads. I'm going to convert that to 3.0 times 10 to the negative 6 farads. I know my potential difference is 12 volts. And I don't know the electrical potential energy, and I don't know the charge on each plate of the capacitor. So those are my unknowns. To find my charge, I can use the equation for capacitance here. I can plug values in and solve for Q. I could also write this as 36 microcoulombs if I wanted to. Either one is correct. Now to find my potential energy, I use the potential energy equation. And I substitute values in to find the electrical potential energy stored in my charged capacitor. And when I multiply that out, I get 2.2 times 10 to the negative 4th joules of energy. Advanced ideas, conceptual challenge on page 678 in your book, your own questions, or try this. For whom was the farad named and why? There's a great question. Probably Michael Faraday. Give you a hint. Look up what he did, some things that he contributed to our understanding of electromagnetic phenomena. Look forward to seeing what you come up with, and we'll see you in class.